Okay, so to solve this problem, we first need to talk about the magnitude of a complex number, which is a very important tool for problems like these. So first, a definition. So you may remember that the absolute value of a real number, which is basically the same as the magnitude of a complex number, can be defined as, just make it positive, but it can also be defined as its distance to from zero on the number line. So -2 and 2 have the same distance to 0. They both have a distance of 2 from 0, and so they're the same absolute value, right? The -2 is still 2 away from 0, just in the other direction. So we extend this idea to complex numbers, which fall on a plane. And basically, a number like over here, we just take its direct distance to the origin. And if we have a number a plus bi, aka it is a across and b up, right? We can use Pythagoras' theorem and get that the magnitude is a squared plus b squared square rooted, right? And so this is how we define the magnitude of a complex number, which is going to be an important tool here. So just to write that down, magnitude of a plus bi, that's not 6, it's b, equals the square root of a squared plus b squared. Okay, so next, it can be shown that the absolute value, or the magnitude, either term works, if you multiply the magnitudes of two complex numbers, that is actually the same as the magnitude of multiplying them. Again, this is very similar to, let's say we had -2 and 3, right? And -2 and 3. This is the same as saying that the absolute value of -2 times the absolute value of 3 is equal to the absolute value of -6, which is true, right? This is 2, this is 3, and this is 6, and 2 times 3 does equal 6. You can do some annoying math to show that it does work for complex numbers, but it's not really necessary here. So this extends really neatly into our next thing we're going to talk about, which is that the absolute, for integers, right, the absolute value, the magnitude of x to the n, of some complex number to the nth power, is equal to the magnitude taken to the nth. So what this is really saying is that, like, the absolute value of -3 cubed is equal to the absolute value of -3 then cubed. And this follows directly from this, right? Because we're really just absolute valuing and then taking a bunch of x's inside, and we can just put absolute values between these is exactly what this problem is saying. It's just a special case. And if you want to work out the math here, this is absolute value of -27 right here. And this is just equal to 27. So they're the same. So we can apply this to say that if that our number z to the fifth has magnitude of the magnitude of z to the fifth right here. Next, notice that the magnitude of a minus bi is the square root of a squared plus -b squared. But since we're squaring it, the negative can go away, which is equal to the square root of a squared plus b squared. And notice this is the same as the magnitude of a plus bi. This right here is the conjugate, which is what we're talking about in this problem. So we can then conclude that the magnitude of z equals the magnitude of what I'm going to call z bar, because it's got a bar over it. Okay, so if two complex numbers are the same number, their magnitudes obviously have to be equal to each other. So we know that the magnitude of z to the fifth equals the magnitude of z bar, because we made this assumption over here. It's the point of the problem. We can use our laws here to show that, well, magnitude of z to the fifth is magnitude of z to the fifth. So magnitude of z to the fifth equals magnitude of z bar, but magnitude of z bar is magnitude of z, as we showed right here. So really, the magnitude of z to the fifth equals z. Okay, so this is a nice equation because we know that these are both real numbers. In fact, they're both positive real numbers. And there are only two non-negative real numbers. There are only two non-negative real numbers that this is true for. You might think there's only one because we can divide out a z here and get z to the magnitude of z to the fourth equals 1, and then we could just say, well, there's only one positive real fourth root of 1, but 0 actually works too, and the bad assumption there is that you can divide by magnitude of z. So our solutions here are magnitude of z is 0 or magnitude of z is 1. Now this case is very nice because there's only one complex number with magnitude 0. So z equals 0. That's one solution, but there might still be other solutions. So what if the magnitude of z is 1? Well, let's look into this. If the magnitude of z is 1, well, let's think about what we know. We know that z to the 5th equals z bar. And we know that z times z bar is a positive real number. You can see this in the problem itself in the introduction to conjugates. So I could write what it's equal to, but we just need to know that it's a positive real number, right? And since, so we can rewrite this as, since z bar equals z to the 5th, we know this is z times z to the 5th is a positive real number, right? And that's obviously z to the 6th. So we know that z to the 6th is a positive real number, and we know that the magnitude of z to the 6th is equal to the magnitude of z to the 6th, again, from up here, from this right here, which is, we're assuming the magnitude of z is 1, so it's 1, right? So z to the 6th right here is a positive real number with magnitude 1. There's only one of those, it's 1. So we now have a great equation, z to the 6th equals 1. This is only in our case where we assume that z equals 1. This case we've already, or the magnitude of z equals 1. This case where magnitude of z is 0, we've already accounted for. Now, this is a theorem that I'm not going to prove here, but you can look it up. There are exactly, for any integer n, for any positive integer n, there are exactly nth roots of 1. So there are exactly n numbers that you can take to get to 1. An example of this is, or that you can take to the nth power to get to 1. An example of this is the 4th roots. So we're dealing with complex numbers in this, to be clear. I mean, this obviously isn't true for non-complex numbers. So for instance, there are 4 4th roots of 1 in complex numbers, right? There's 1, obviously, 1 to the 4th equals 1, negative 1, negative 1 to the 4th equals 1. There's I to the 4th equals 1, and there's also negative I. So there are 4 4th roots, and this extends to any positive number, including 6. So there are 6 6th roots of 1, right? And notice that all 6 of these would solve this equation right here. Obviously, because what it means to be a 6th root of 1 is that when you take it to the 6th power, you get 1. So these are all solutions here, and these also all solve for our original equation here. We could find them. You can use some basic trig, but it's really not necessary because the question only asks how many there are. So we've narrowed it down to 6 solutions in the case that magnitude of z is 1, and another extra solution in the case that it's 0. And so our final answer is 6 plus 1, 7 solutions total.